Okay, heat capacity. Heat capacity is defined as the amount of heat required to rise the temperature of a substance by 1 degree Celsius. Heat capacity is defined as the amount of heat required to rise the temperature of a substance by 1 degree Celsius. If 1 gram of the substance is taken, then it is called specific heat capacity. And if 1 mole of the substance is taken, then it is called molar heat capacity. Heat capacity is specific heat capacity and molar heat capacity. Heat capacity is defined as the amount of heat required to rise the temperature of substance by 1 degree Celsius. If 1 gram of the substance is taken, then it is called specific heat capacity. And if 1 mole of the substance is taken, then it is called molar heat capacity. The amount of heat dq required to rise a certain temperature of a substance is directly proportional to its mass. dq proportional, equation first. The amount of heat dq required for the same mass of substance is directly proportional to rise in temperature dt. dt is rise in temperature and dt equal to T2 minus T1. From equation first and second, dq proportional m dt, so dq equal to mc dt. Equation third. A specific heat capacity, the amount of heat required to rise the temperature of 1 gram of substance by 1 degree Celsius is called specific heat capacity. Molar heat capacity, the amount of heat required to rise the temperature of 1 mole of substance by 1 degree Celsius is called molar heat capacity. Molar heat capacity can be measured either at constant pressure or a constant volume are called molar heat capacity at constant pressure and molar heat capacity at constant volume are denoted by Cp and Cv respectively. From equation third, dq equal to mc dt, C equal to dq over dt. C is the molar heat capacity if 1 mole of substance is taken. Molar heat capacity at constant pressure, the amount of heat required to rise the temperature of 1 mole of substance by 1 degree Celsius is called molar heat capacity and denoted by Cp. Molar heat is supplied to a system at constant pressure. Then temperature increase and some work is done. From the first law of thermodynamics, dq equal to dE plus pdV. Substituting the value of dq in equation 4, we get C equal to dq over dt, dq, dE plus pdV. dE plus pd over dt. At constant pressure, Cp equal to d over dtp plus p dv over dt, be equation 6. In terms of partial derivatives, equation 6 can be expressed Cp equal to dava E over dava T, P plus P dava V over dava TV, equation 7. We know that as equal to E plus PV. Differentiating the equation with respect to temperature at constant pressure, we get delta S over delta Tp equal to delta E over delta Tp plus P delta V over delta Tv, equation 8. From equation 6 and 8, we get Cp equal to delta S over delta Tp. In terms of infinitesimal change, equation 9 can be written as Cp equal to ds over dt. Heat capacity at constant pressure is defined as the rate of heat constant enthalpy with rise in temperature at constant pressure. Molar heat capacity at constant volume Cv. Molar heat capacity at constant volume are called molar heat capacity at constant volume Cv and denoted. Okay, the molar heat capacity at constant volume is called the molar heat capacity at constant volume and denoted by Cv. From the equation 5, C equal to dq over dt. So we can write dq d plus p dv over dt at constant dv equal to 0. So C equal to d over dt v. In terms of partial pressure, Cv equal to delta E over delta Tv. In terms of infinitesimal change equation, xi can be written as Cv equal to d over dt. Relationship between Cp and Cv, we know that C equal to dq over dt equation first. From the first law of thermodynamics, dq equal to d plus pdv, substituting the value of dq in equation IB, we get C equal to dq over dt d plus pdv over dt equation third. At constant pressure, Cp equal to d over dt p plus p dv over dt v. In terms of partial derivative equation, 6 can be expressed as Cp equal to delta E over delta Tp plus P delta V over delta Tv. At constant volume, delta V equal to 0. Equation IB becomes Cv equal to delta V over delta Tv. Subtracting the equation Bi from equation B, Cp minus Cv equal to delta E over delta Tp plus P delta V over delta Tv minus delta E over delta Tv. Internal energy E is the state function. It is the function of temperature, pressure, and volume. At constant pressure is the function of temperature and volume, that is E equal to EFTV. Since the internal energy is state function, it has the exact differential D equal to W over TV dt plus P W T dV. Since internal energy is the function of the temperature, at constant temperature, the variation of internal energy with volume is 0, that is W over Vt dV equal to 0. Now equation BII becomes at constant pressure, so D equal to W over Tp dt. Now the equation BII becomes at constant volume, so D equal to W over Tv dt. So W over Tv dt equal to W over Tp dt. So we can write dt dt cancel. So W over Tv equal to W over Tp. Now from equation Bi becomes Cp minus Cv equal to W over Tp plus P plus W over Tv minus W over T. P equation Bi. In solving, we get Cp minus Cv equal to P over W over Tv. For 1 mole of the gas, the ideal gas equation PV equal to RT. So differentiating the equation with respect to temperature at constant pressure. So P equal to P W over T P equal to R T T P. So R equal to P W T P. from the equation X, Cp minus Cv equal to P double V double Tb. So you can conclude that Cp minus Cv equal to R.